Welcome and settle in. Imagine yourself drifting slowly through a quiet, starlit expanse. Your breathing easy and unhurried, your thoughts resting like soft dust on a calm surface. Tonight, we'll wander together through a gentle story about interstellar dust, about its slow, patient drift, and how, almost without anyone noticing, it becomes the quiet sculptor of new solar systems. If you enjoy resting to calm science, please tap like and subscribe so more sleepy journeys find their way to you. And feel free to open the playlist link in the description to keep learning softly while you drift. How sleepy are you on a scale of 1 to 10? Let the scene form in your imagination. You find yourself riding on a tiny grain, smaller than a whisper, a fleck of ancient mineral and carbon. Around you, the darkness is not empty. It is a deep, velvety sea with a faint shimmer, like a room where someone has pulled sheer curtains across a window. Starlight reaches you as a muted glow. Some of it slides along your surface, some is scattered away, and a little bit warms you, imperceptibly, like a breath against cool glass. You are drifting, unhurried, unbothered, guided by forces as soft as the weight of a falling feather. Interstellar dust grains are humble things. Many are silicates, cousins of familiar minerals in rocks on Earth, tiny fragments of olivine and pyroxene sprinkled with iron. Others are carbon-rich like soot or graphite, sometimes layered like pages in a very thin book, sometimes rounded like tiny beads. Some grains carry coats of ice, water, carbon monoxide, methanol, ammonia, thin mantles that form when the gas between stars grows cold and dense. Most grains are far smaller than a strand of hair, smaller than a mote caught in a sunbeam through a quiet window. Some are so small they are hardly larger than big molecules. Others reach a few micrometers across, like powdery snowflakes that never melt. Imagine yourself floating between stars in a region where the gas is thin and the temperature is low. Here, dust grains take their time. They drift with the gas. They feel the push of light from nearby stars. They trace the magnetic fields like leaves following gentle currents in a pond. The journey each grain takes is long. It can last millions of years. There is no rush in this place. The gentle rhythm continues like a slow tide. You might picture where these grains were born. Some came from the cool winds of old stars, released like seeds from a dandelion puff, carried outwards and left to wander. Some were forged in the afterglow of stellar endings, their raw materials condensed from hot vapors into solid forms. But those fierce moments have passed. What remains here is the calm aftermath, the softened particles that time has worn smooth like pebbles in a stream. Radiation slowly changes their surfaces. Tiny impacts from atoms and cosmic rays decorate them with subtle pits. Ices freeze onto them, melt off, freeze again over cycles of quiet. In the gentle shade cast by a dust cloud, chemistry relaxes into existence. Hydrogen atoms settle onto cold grain surfaces, meet and pair up as H2, a simple common molecule that loves the quiet. Atoms of carbon, oxygen, nitrogen, and sulfur find one another, one step at a time, anchored by the grain surface like a small stage where molecules can practice their lines. Little by little, simple molecules become slightly more complex. Methanol joins, ammonia joins, and longer chains begin to form under the soft influence of starlight filtered through dust. It is not loud chemistry, it is lazy chemistry, patient and unassuming, the kind that makes the air feel almost perfumed with possibility, though there is no smell at all. As dust accumulates in certain regions, the gas around it cools more effectively. Dust is good at radiating away heat, at letting energy drift off as faint light. In a dense cloud, this cooling helps gravity to speak more clearly. Over time, over spans so long that even stars would call them leisurely, parts of a cloud become slightly heavier than their surroundings. They begin to fall inward, very slowly. Imagine watching fog sink into a valley at dusk. The dust is there, bearing witness, absorbing light that would otherwise heat the gas. The cloud grows a little colder, a little denser, and the whisper of collapse continues. Imagine the cloud gently turning. The universe likes a little spin, and even a tiny rotation will eventually show itself. As the slow tumble becomes a subtle disk, dust and gas settle into a thin, flat shape, like a band of soft smoke floating around a dawn lantern. You're still drifting on your grain, perched at the start of something. In this new, smooth disk, particles begin to meet. The gentle rhythm continues. They tap, they touch, they stick, sometimes by the shy pull of van der Waals forces, the quiet attraction that holds geckos to walls and fingers to frosted glass. Many encounters are so slow and cushioned by the surrounding gas that they result in nothing more than a delicate hello, a tiny kiss, and a rebound. But often, especially when the grains are coated in ices that make them a little sticky, those taps become embraces. Two grains become a cluster. The cluster meets another. Fluff builds. Clumps billow. They grow into something like soft soot snowballs, porous and faint, drifting like thistledown through the disk. If you listen closely to this picture, there is a murmur of gentle forces. Gas flows inward under gravity, spiraling very slowly toward the center where a young star is growing. Dust feels a headwind because the gas is held up slightly by pressure. The gas circles the star just a bit slower than the pure orbital speed of a grain. That tiny difference feels like a mild breeze to the drifting grain, a persistent whisper that nudges it inward. This is radial drift, a simple, steady, patient motion that carries grains from the outer disk toward the warmer regions inside. The journey can be brisk on cosmic terms. Some grains can drift inward over thousands of years, but to you, imagining the path while cozy in bed, it is tranquil. A slow current carries you along. You pass through soft rings in the disk, regions where pressure in the gas piles up. These pressure bumps gather dust like eddies, gather leaves. In them, grains collect and linger, sheltered from the headwind, just as seeds pile up against a fence in a gentle breeze. Imagine yourself hovering above this disk and looking down with quiet eyes. You would see subtle bands, rings and gaps, delicate markings left by pressure structures, and the earliest hints of newborn planets. The disk is not smooth, but faintly rippled. A light dusting of frost lives beyond certain distances from the star, where heat is lower. At each snow line, different ices can exist. There is the water snow line, often closer in, where water transitions from ice to vapor. Farther out, there are lines for carbon monoxide, carbon dioxide, ammonia, and other volatiles. The grain community changes character at each boundary. Ices help grains stick better, like soft glue, making growth easier and collisions more forgiving. The gentle rhythm continues, and the slow ballet of sticking and settling goes on and on. In this quiet theater, the seeds of planets form, not in a rush, not with a bang, but with the steady confidence of dust that knows it can take its time. Fluffy piles become pebbles, and pebbles travel as a kind of linked convoy, moving with the gas and sometimes together faster than the gas, letting shared gravity and drag weave them into tighter bundles. In some places, the crowding becomes meaningful. Tiny variations in motion concentrate solids into filaments and swirls. The pebbles begin to feel each other more strongly than they feel the surrounding gas. Like a school of fish turning together in a calm sea, in a process scientists call the streaming instability, but which you may imagine simply as a quiet gathering. These pebbles collect so densely that gravity has something to hold on to. Clumps collapse, yielding planetesimals, the first true bodies with their own gentle presence, big enough to carry their own gravity, not just passively follow the flow. All this time, the young star in the center is brightening softly, warming the inner disk. Light filters through dust in complex ways. Tiny grains scatter blue light more than red, giving distant clouds a faint bluish sheen when lit from the side, and causing starlight passing through dust to redden like sunlight at sunset. If you could float in the mid-plane of the disk, the light would be dim and gold, hushed into warmth by the grains around you. Your breath would rise as silver mist in this imagined scene, and it would immediately disappear into the cold. At the smallest scales, dust grains carry little charges. They become slightly positive or negative in response to ultraviolet light and stray electrons. These charges let the grains respond to the galaxy's magnetic fields. They can align like tiny compass needles, and from far away, this alignment leaves a fingerprint on the light they absorb and emit. Polarized starlight from a dust cloud is like a faint pattern on silk, telling us something about the direction and shape of invisible fields. There is comfort in the idea that even the hidden things, like magnetism threading through space, find a way to leave gentle signatures if you take the time to look. The story of interstellar dust is also a story of cycles. Many grains are ancient, in meteorites found on Earth, quiet stones that fell from the sky and waited in the dark for someone to pick them up. We find tiny pieces that predate our sun. Some of these pre-solar grains are silicon carbide with unusual isotopes. Others are graphite with trapped noble gases. And some are even nanodiamonds, a word that sounds grand for something so very small. Their isotopic patterns are like regional accents in the language of atoms, letting us know they were formed in different kinds of stars. These grains survived the birth of our solar system. They survived the heat of disks and the tumble of time. They arrived here, still carrying whispers from their home stars, as if the universe tucked love notes into the pebbles that would later build planets. Imagine yourself walking a quiet path at night, the air cool and still. Overhead, a streak of pale light marks the sky. Even meteors, in their brief show, are part of this gentle cycle. Most of them are the size of sand grains, drifting through space until they meet Earth's atmosphere and glow softly for a heartbeat. Much of the haze we see around the zodiac, that faint triangle of light before sunrise or after sunset, is reflected sunlight from a cloud of dust that lives in the inner solar system. It is not dramatic, hardly noticeable from a city, but under dark skies, it is like a ghostly candle held up to the plane of our planetary family. Returning to the disk, imagine the passage of time as a slow breeze. In the inner regions, close to the star, some grains are warmed until their ices vanish. Others collide and shatter, redistributing their material back to smaller sizes. The disk is a place of balance, a delicate exchange between building up and breaking down. But overall, the shape of the story bends toward growth. The gentle rhythm continues. Tiny bits make slightly larger bits, and those become pebbles and then rocks, and sometimes kilometer-sized bodies that drift not as dust anymore, but as quiet travelers with names and paths. These early worlds often tell the disk what to do, carving gullies and rings, shepherding dust into arcs and crescents. If you look with careful eyes, as astronomers do, with arrays of radio dishes arranged over mountain deserts, you see the disk structure, dark rings where dust is missing, bright rings where it is gathered, spiral arms like faint fingerprints. Each detail is the soft echo of gravity at work. Even where we cannot see the planets directly, their influence is present, as if they move under a thick blanket, their shapes known by how the blanket folds and settles. Consider the snow lines again, those quiet thresholds in temperature. They mark where water ice can exist and farther out, where carbon monoxide ice can survive. The presence of ice changes everything, making grains stick more easily and move differently. It also changes composition, seeding the inner regions with the gases evaporated from icy grains as they drift inward. This soft delivery can enrich the inner disk with water and carbon compounds that might otherwise be trapped far away. There is a steady, almost homey feeling to this inward migration, like a slow conveyor bringing ingredients from a chilly pantry to the warm stove of planet making. As pebbles grow, some bodies capture them efficiently, like gentle nets sweeping through a cloud. This process, called pebble accretion, is less like a dramatic collision and more like a slow gathering. A growing core's gravity and the drag of the gas around it combine to guide pebbles into orbits that lead to capture, even with small relative speeds. Over time, this mode of feeding can build planetary cores much faster than older ideas imagined, especially where the disk is thick with pebbles and the gas is dense. Yet even here, you can picture the process as peaceful, a rain of little shadows settling onto a patient, silent surface, one by one. Sometimes dust that has grown too quickly or drifted too far is replenished by collisions and shattering, returning substance to the small grain reservoir. Even in this, there is balance. The smallest grains, which are best at interacting with light, are continually created again. They maintain the disk's soft glow, its ability to absorb and re-emit energy, to keep cooling and chemistry in tune. Dust is the thermostat and the canvas, the cushion and the brush. Wherever it goes, it changes how energy moves, how molecules form, how solids gather. If you could hear the faintest murmurs of the disk, you might make out a kind of lullaby. There is the sigh of gas sliding past dust, the smallest rasp of particles kissing and parting, the hush of heat leaving in long wavelengths. Like a low hum, the music is slow and consistent. The gentle rhythm continues. In the vast, thin spaces between stars, dust can drift for a long while before it finds a home, Magnetic irregularities and waves in the plasma gently shepherd it into filaments. Slight differences in density produce a network like a lacework of mist. Regions of greater density are protected from the harshest starlight. In these sheltered pockets, molecules can persist and grow. They are nurseries in waiting. Gravity circles them with calm attention, patient as ever. From time to time, a nearby star's light pushes on the smallest grains, nudging them outward, away from the light. Radiation pressure is not dramatic on a human scale, but over long distances, it matters. It makes halos around young stars, thins out dust in some directions, and populates the outskirts with a faint population of wanderers. In other places, where the gas is moving inward more quickly, dust can pile up like a slow dune forming in the lee of a light breeze. Eddies in gas flow can create small traps, swirling pools where grains gather and wait. Think about the way dust interacts with the bathed light from stars and warm gas. At short wavelengths, grains absorb ultraviolet light and kick out electrons. Those energetic electrons wander off into the gas, heating it a little, maintaining a delicate balance of temperatures. At longer wavelengths, grains radiate away their warmth, glowing softly in the far infrared or in millimeter light. Observatories with eyes tuned to these wavelengths trace dust, like a painter tracing a shoreline, filling in where gas is hard to see. These maps show rings and arcs. They show where dust is thin and where it is thick. They show the imprints of planets we cannot yet pick out directly, each one like the quiet shape of a fish moving beneath a calm lake. Dust grains do more than just collect, they also obscure. Over large distances, dust dims and reddens background stars. It makes the band of a galaxy look mottled and streaked, weaving patterns that were once mistaken for empty spaces. Now, we know that those dark lanes are highways of cool matter, places where the future is collecting itself softly and carefully. The dark is not empty. It is full of small, hidden things, busy at a moderate, unhurried pace. If you have ever watched clouds build at the edge of an autumn afternoon, you know the feeling of such slow arrangement, the quiet readiness in the air. In the earliest chapters of a solar system, dust sets the stage for fine distinctions. What grains end up where depends on their size, their composition, the turbulence of the gas, and the structure of pressure in the disk. Small grains travel with the gas, stirred up and down, in and out. Larger grains settle into the midplane and feel the headwind more strongly. This size sorting is like sifting flour through a sieve with many meshes. The finest grains are suspended, visible as a diffuse haze. The coarser ones drop into a thin, dense layer, a sheet of soft powder, ready for building. Over time, turbulence calms. The thickness of the dust layer shrinks. Collisions become more frequent, and growth accelerates. You could think of it like snowfall settling into a firmer blanket as night advances and the air grows still. Even the chemistry of dust changes. In cold, shaded places, ices accumulate and simple molecules are preserved. Layer upon layer, like rings in a tree, the mantles on grains record the history of light and shadow, warm and cold. When heat later returns, maybe because the grain drifts inward or because a nearby young star flares a little, some of those ices release their molecules back into the gas. where they can be detected as faint signatures in spectra. The details of which molecules exist will tell us about the journey the dust has taken. It is a book written in quiet script, a bedtime story written in lines of faint emission. At times, a grain's path leads it into shocks where gas speeds change abruptly, perhaps because of spiral density waves or the wake of a forming planet. Even then, the experience is more like a jostle than a blow. Heating can be modest. Some ices may be lost. The grain may be reshaped. But often, it drifts on, carrying with it the memory of a jolt, a change in its mineral structure, a tiny glassy bead where it once was crystalline. Later, as planetesimals grow and heating becomes more local, these transformations can record the subtle details of that environment. On Earth, pieces of such history can be found in chondrites, meteorites that arrived quietly one day, sat in the soil, and patiently waited to tell their story. Imagine that you could hold a small chondrite in your hand in a silent museum room, the air calm and the lights soft. Within, you would find tiny spheres called chondrules, likely formed in flash heating events in the early disk, set in a matrix of fine dust that never melted. There would be calcium aluminum-rich inclusions, ancient pieces that condensed early, and fragments of pre-solar grains that slipped in from elsewhere. Even the voids in the rock would tell you about the gases that once flowed where those grains lived, their chemical fingerprints captured in the shapes that remained. The rock is a gentle archive. It contains seas of memory compressed into a quiet weight. If you wonder about the origin of water here on Earth or the source of carbon for life, you can listen to dust and ice for hints. Beyond the water snow line, grains build up thick coats of ice. As they drift inward, they carry water into warmer regions, releasing it when the ambient temperature rises. Some of that water finds its way onto growing planetesimals. Later, those bodies deliver water to inner worlds through soft collisions across geological time. A similar journey happens for many carbon compounds and nitrogen-bearing molecules. Over time, ingredients collect where they were sparse, and beginnings become possible. The quiet delivery of materials is not just a mechanical process. It is the slow setting of a table for chemistry that loves to explore. The growth of gas giants has its own gentle tempo. In the outer disk beyond the snow lines, cores can form more quickly because ices increase the amount of solid material and allow grains to stick better. Once a core reaches a certain size, it can begin to draw in the surrounding gas, at first softly, then more decisively. But even this can be imagined as the slow inflation of a bubble, as the planet wraps itself in an atmosphere drawn from the disk. Rings and gaps appear, narrow passages where dust is shepherded into arcs, and accompanying the formation of these giants, smaller worlds find stable niches. The entire system is a quiet dance of trade-offs and balances, where the brightness of the central star, the mass of the disk, and the flow of dust work together over long afternoons of cosmic time. Another layer of this story is alignment and polarization. Dust grains, not perfect spheres, feel torques from starlight, small twisting nudges that make them spin and align with magnetic fields through radiative torque alignment. A calm breeze you cannot feel directly, but you can see the result if you watch how light is affected. From this, astronomers can read the layout of magnetic fields and their role in helping or resisting collapse in clouds where stars are forming. The fields thread through the dust like gossamer lines through lace, delicate and real. No abrupt motions are needed to understand them. The quiet mathematics of polarization, of angles and intensities, and subtle wavelength dependence is its own unhurried story. When we look farther into other galaxies, we see the same themes, dust lanes tracing spiral arms, marking where gas is densest, shielding new stars and their disks from harsh light so that they can form. In star-bursting regions, dust glows with the warmth of all the young stars' light, re-emitted in longer wavelengths. It softens the portraits of galaxies, giving them depth and texture. Where dust dims the light, it also allows the interior to cool and settle, making the conditions for stars and planets to emerge. The same gentle sculptor is at work, on scales of hundreds of light years out to the rims of galaxies where the edges fade into the quiet between galaxy clusters. Closer to home, dust continues its work in our own solar system. The zodiacal cloud, a veil of fine grains orbiting the sun, is fed by comets that shed material gently as they warm, and by the grinding down of asteroids in slow collisions. Grains in this inner region feel the faint tug of pointing Robertson drag, a soft retarding force caused by their own emission of radiation as they move through sunlight. This drag makes them spiral inward slowly, like tiny leaves circling a drain so wide that you cannot see the center. Some grains are nudged into resonances with planets, forming softly enhanced rings that trail or lead, while others simply continue their quiet inward journey until they vanish into sunlight. In the thin atmosphere of the Earth, incoming dust, much of it microscopic, becomes meteors and meteor smoke, delicate particles that drift down and contribute to the highest clouds. You might never notice them, though sometimes noctilucent clouds in summer twilight hint at their presence, as though the sky is made of brushed aluminum. It is another small way that the universe's very fine things, having traveled for so long, lean gently into our world. Imagine yourself returning to that protoplanetary disk, now older by a few million years. Much of the gas has drifted away or been cleared. Dust that did not become part of larger bodies is sparser. Planetary embryos have grown. Their orbits are newly settled, like a family that has just moved into a home and placed its furniture. There are belts of leftover materials at the edges, places where dust and ice still collide and crumble, backfilling a small inventory of fine grains that shimmer in the thin light. The gentle rhythm continues, but it is a different tune, slower and quieter still. Within some of these newborn planetary systems, collisions between larger bodies stir up dust, creating warm debris disks that glow in infrared light. But that glow is not a bonfire, it is a soft ember. Over time, these reserves of dust wane as planets sweep their surroundings clean. What remains can be a reminder of the early craftsmen who shaped the system. Thin bands of tiny stones and frost, rings that speak of shepherds, apps that hint at bridges and quiet traffic lanes. Our own solar system bears these marks. The asteroid belt is a library of leftover material, its dust constantly refreshed by gentle grinding. The Kuiper belt beyond Neptune holds icy bodies that whisper of early conditions far from the sun. Comets, when they approach, release dust that spreads into tails and trails, marking their wandering paths. In meteorites, we read the chemical gradients that existed in the disk long ago. Water-rich carbonaceous chondrites speak of cooler birthplaces, drier chondrites speak of hotter ones. Even the differences in oxygen isotopes tell a calm tale of reservoirs that were once separate, later mixed by slow drifts and mild flows. Some of the dust stories about light's quiet biases. Small grains, especially those with sizes comparable to the wavelengths of visible light, scatter shorter wavelengths more efficiently. That is why reflection nebulae appear blue, colored by scattered light, not by any intrinsic hue. At longer wavelengths, where grains are small compared to the light's reach, the scattering and absorption behave differently, and we learn about grain sizes by how the color of light changes with direction and distance. It is like watching how fog near a lake takes on a golden tone at sunset, not because the fog itself is yellow, but because of the way light travels through it and back to your soft gaze. As you drift toward the midpoint of this journey, let your thoughts become even lighter, as if you were a feather hanging in slow air. Still awake? Comment the secret word, nebula. Now imagine a crisp, dark observatory, perhaps high on a mountain, where a radio telescope listens with calm persistence to the faint glow from dust at millimeter wavelengths. The air is thin, and the world below is quiet. Observers watch as rings and spirals emerge in their data, not as dramatic photographs, but as softly shaded maps, contours of brightness coded into gentle colors. Each ring whispers about a pressure bump. Each shadow suggests an unseen shepherd. Far away, another instrument watches in the infrared, finding ice lines by their spectral signatures, lines that mark where molecules can freeze or where they sublimate. From these lines and shapes, we infer the physics that dust has followed, almost the way you could infer the shape of a riverbed by looking at the water's surface from a slow-moving boat. In laboratories, under lights that hum faintly, scientists grow analog dust in vacuum chambers. They coat cold grains with ices, then warm them as ultraviolet lamps shine gently. The experiments reveal which molecules form and which break apart, how sticky ice makes collisions, how grains charge and discharge. In one corner, a device measures how tiny particles stick when they meet at millimeters per second. The results speak softly of thresholds, of when bouncing wins and when sticking does, of what happens when grains become large enough to roll and tumble rather than simply meet and stop. The conclusions find their way back to models of disks, of how fast grains drift and how they grow, and the models give predictions to test with quiet telescopes under silent skies. Consider the dust's influence on a planet's later habitability. If dust carried water inward, and if some of that water found its way to a rocky surface, and if an atmosphere formed, then dust had a hand in making a world where clouds could rain and oceans could lie still under a pale moon. The mineral composition of dust influences the elements available on a planet, shaping the rocks that will weather and the nutrients that plants, one day far later, might draw from soil. Even the presence of certain elements in the right proportions, like iron and nickel, can be traced back to what dust brought, to how it was distributed, to what gentle currents carried it where. Time passes in this narrative without urgency. The disk evolves. Grains change companions and neighborhoods. Some lucky pebbles are captured by growing worlds. Others drift and drift until they reach the warm inner regions and evaporate, redistributing their material into the gas phase, which later drifts again. Dust goes from being a free wanderer to being part of something bigger, and that, ultimately, is the essence of this story. The union of small things into larger things, and the quiet confidence that such unions, countless and soft, can build worlds. In more distant systems, we witness the same patterns. Donut-like disks with rings upon rings, spiral arms that betray the presence of a companion, narrow gaps where small planets likely orbit, humming to themselves like sleepy bees. These features are not unique to any one star. They are of the consistent handwriting of physics, traced by dust in lines that are pleasingly familiar from one system to the next. When we look back at our own sky where the Milky Way arches over in a soft band, we know that in countless places along that band, dust is working. New planets are quietly being cut and polished from the tangle of small stuff drifting close to newborn suns. The smallest grains are not always passive. Some grains are polycyclic aromatic hydrocarbons, flat, carbon-rich molecules with ring-like structures. They absorb ultraviolet light and fluoresce in the infrared, leaving distinctive fingerprints. These features tell us about the radiation environment, about how hard the local photons press on matter. Where the features are bright, we know the light is eager. Where they are weak, the light is gentle. These molecules are part of the tapestry, filling in the gaps between larger grains, providing surfaces for chemistry that would otherwise be slow. In your mind's eye, they are like confetti so small you can't see each piece, but together they create a faint shimmer in the darkness. Sometimes dust aligns in structures large enough to be visible, filaments that stretch across star-forming regions. These filaments are like the veins in a leaf, carrying gas and dust to the forming cores where stars will eventually grow. At the intersections, the densest knots quietly expand their influence. Eventually, thermally and gravitationally, a star is born. That process, while energetic in its details, is measured in so many slow steps that the overall mood is serene. Where the star forms, the surrounding dust remains close, creating a cocoon that shapes the early light, softening it like curtains across a dawn window. When disks thin out and planets assert themselves, dust is no longer the main actor on the stage, but it remains a narrator, a commentator letting us know where to look. If a young planet is hot, it might glow faintly, and dust around it will respond, marking its presence. If a giant planet opens a gap, dust piled at the edges tells us the gap is there. Where two planets interact, resonances create patterns at multiples of their orbital periods, leaving ripples that dust will fill and which patient observers can map. In the fullness of time, dust becomes part of the surfaces of moons, of rings around outer planets, and of the fine material in faintly glowing tori. It is not only an ingredient of beginnings, it is a gardener that keeps returning to tidy and arrange even long after the main work seems done. The faint rings around Jupiter, Saturn, Uranus, and Neptune are fed by dust from small impacts and from the surfaces of tiny moons, and this dust traces the gravity of each system's architecture. The patterns are slender and delicate. Observed backlit by the sun, they look like hairlines in glass. At the scale of galaxies, dust plays yet another role. It hides some of the youngest stars, making them visible only in infrared light. Where dust is absent or thin, galaxies appear more transparent, like a piece of silk stretched taut. The cosmic background light we see also passes through dust on its way, reddened and dimmed just a little. These effects are not nuisances, they are information. They tell us where matter has gathered, where wind and radiation have moved it, where to look for the origami of structures folding and unfolding over billions of years. Take a gentle breath and imagine the smell of cool metal and faint snow, like the interior of a quiet spacecraft that has just opened its door to a shaded cavern. It is a pretend smell, a borrowed sensation, just to help you sit with the idea of dust in cold space. The surfaces of grains coated with ices would feel like powdered glass under a glove. Their touch would be dry and whispers soft. In the throat of time, they are the grit that becomes pearls. Precellar grains in meteorites are among the most intimate storytellers in this topic. They carry isotopic compositions that do not match those of our solar system, indicating that they formed in other stars with different nuclear histories. The spread in silicon isotopes in silicon carbide, or the strange xenon patterns in nanodiamonds, speak of supernovae or asymptotic giant branch stars. To hold such a grain would be to hold a message older than the Earth itself. Yet these messages are not loud proclamations. They are gentle differences in the ratios of isotopes, subtle features in mass spectrometry peaks, little hills and valleys that blink up on instruments under the soft hum of laboratory fans. The physics that underlies all of this is comfortable and steady. Gas drag is the modest friction that slows a grain drifting through gas. Pressure gradients are the slight differences in gas density that make some places easier for dust to stay. Turbulence, instead of being a roar, can be thought of as a field of small, whispering eddies, each turning in place, sometimes lifting grains, sometimes letting them rest. Gravity is consistent and patient. It waits, and when enough material gathers, it acts. But it does not rush. You can think of interstellar dust as the orchestra's string section in a piece of music that features many instruments. It provides a bass texture, a consistent tone. It responds to the conductor's cues, light, magnetism, gas flow, without pushing the tempo. Other sections, like stars and planets, may take solos later, but the strings carry the melody of formation from start to finish, gentle and present, the way a lullaby returns to the same refrain over and over. The gentle rhythm continues. As you rest, you might wonder how we know so much about tiny, quiet things so far away. The answer is in accumulation, like dust itself. Our knowledge grows by small pieces that stick together. Observations in many wavelengths, models run with care, laboratory experiments, meteorite studies, and the echo of theory in quiet equations that tell us how drag and pressure and gravity set the pace. When the pieces agree, we see the outline of truth. When they disagree, we wait and watch and test again, like a gardener who learns the habits of a plant by returning to it each morning. Dust is also a mediator in the dance between starlight and gas. It absorbs ultraviolet light and protects molecules from harsh radiation. It lets gas cool through emission. It seeds the formation of stars by enabling molecules to form, and of planets by providing the building material and by controlling how that material moves. The progress from dust to disk to planet is not an abrupt transition. It is a spectrum of states, each one overlapping, each one filled with minor influences that add up when you let them. Where does the story go after planets form? In some places, dust continues to be born from the erosion of asteroid belts and the outgassing of comets, sustaining debris disks around mature stars. Such disks slowly wane as material is removed. The rate of dust production gently declines, the light fades, and what remains is a quiet background. Occasional events can increase the dust for a while, but those are rare. The overall story is of dwindling and calm. In the far future, the dust created in systems like ours will again drift out into the interstellar medium, part of it ejected by star winds, part of it nudged away by light. It will join the broader family of dust between the stars to be cycled yet again into new molecular clouds and new disks, to become someday part of worlds not yet imagined. It is a comforting thought, the way a stream loops back into a lake. Nothing is wasted. Everything is invited to be used again. When you consider our own bodies, made of elements forged in stars, there is a quiet echo of dust there too. Some of the atoms in you likely spent time on grain surfaces, move in and out of ices, were coated and stripped, warmed and cooled. The gentle drift that built solar systems also handled the ingredients that would become you. There is nothing dramatic in this thought. It is merely a soft reassurance that you belong here as much as the stars do, and that the same patient processes that built planets attended to you in their way over long, long mornings of time. Listen to the last chapters of this story as if you were listening to rain on a roof, each drop a small fact falling quietly. Dust grains respond to starlight with a slight push. They respond to gas with a slight pull. They move inward when nothing stops them, outward when light insists. They become sticky with ice beyond snow lines, and they are more brittle close to the star. They align with magnetic fields and polarize light. They redden starlight and warm gently with absorbed energy. They seed molecules and bear witness to isotopic histories. They are carried into planetesimals, then planets, then sometimes into atmospheres or ring systems or ocean-bound meteors. They drift, they gather, they vanish, they reappear. If you find yourself getting drowsy, let these descriptions wash over you without effort. You don't need to carry them all. Imagine instead a single soft picture, a pale disk around a faint young star, thin as tissue, glimmering slightly. Dust moves within it as if under the slow breath of a sleeping giant, tides of motion so calm that even the concept of motion seems too lively. In that disk, at many scales, the foundations of a solar system are placed low and steady without flourish. In very cold places, one can imagine the smell of clean frost, the way cold seems to have a scent, even though it does not. It is a human comfort to attach senses to the unseen, to give your mind something to hold. Dust gives you something to hold too, a concept easy to picture. A tiny mote-like object, a floating piece of rock or carbon, just big enough to catch a beam of light and make it visible. When you see a sunbeam in your room, the motes are not interstellar, but the feeling is the same, light made visible by small things. The universe is full of this. Beyond the technicalities, there is a mood to this subject that suits sleep. The slowness of drift, the patience of accumulation, the long intervals between meaningful changes. Dust's journey is free of drama most of the time. It is a persistent, quiet effort, which is exactly how so much of reality proceeds. Leaves fall, snow layers, stones weather, dust drifts. The gentle rhythm continues. For a while now, we have followed that rhythm across many scenes. We rode a grain through interstellar space, through a collapsing cloud, into a disk along pressure bumps, past snow lines, into pebbles, and from there into planetesimals. We peered at disks with long wavelength eyes and watched them with polarizing glasses. We held meteorites and looked inside them for pre-solar grains. We imagined dust glowing in galaxies and dimming starlight across the sky. We watched comets shed dust and planets shepherd rings. We allowed ourselves to rest in the idea that small, patient things multiply their kindnesses over time. You might notice your breathing is calmer now. Let your shoulders drop a little. Imagine the universe wide and supportive, like a warm blanket with a subtle weight. The stars are far away, but their light, softened by dust, reaches you as a memory. It is all right to let your attention wander. It is all right to drift. As you return slowly to the room where you are, the dust on your shelf or windowsill may look different. It, too, is a form of history, the gathering of tiny things over time, on a nightstand, on a book. It forms a thin layer that records stillness and the passing of days. On a cosmic scale, the dust is the same idea with different materials and centuries written in. It makes reality legible. It shows us where things have moved and where they have stayed. You have been listening to a quiet story heavy with small details and long times, a story that invites your mind to soften. If your eyes close now, the disk will keep turning and dust will keep drifting, and new solar systems will continue to be shaped by the tiniest sculptors, their patient hands everywhere and nowhere. You can rest knowing that the universe proceeds on schedule, unhurried, content to take the long way to beautiful outcomes. Thank you for spending this gentle time together. If this helped you relax, please consider subscribing and leaving a like so we can keep releasing calm science videos this often. There is a playlist waiting in the description if you want to keep learning in the background while you drift. For now, you can let go and let the quiet sculptors do their work as the gentle rhythm continues and sleep arrives, slow and kind.